Okay, so now we're ready to start some more complicated examples with the second derivative test. So in the last couple videos we did an intro with the second derivative test. We talked about what it is and kind of why it works. And then we looked at some simple examples that illustrate the possibilities. Now we'll do a more complicated example. Basically we're just going to find where the local extrema occur for this function f of x equals x cubed minus 3x. So again, when we say where the extrema occur, that just means the x values. We don't really care about the y values for this example. Because if you want to find the y values, just take your x values that you get, plug them into the original function. And what we just want to do here is illustrate the differences between the second derivative test and first derivative test. So we only need to be concerned with the x values for that. So anyway, this is a function that we used when we did examples for the first derivative test. There's going to be a link to that in the description for this video, so go ahead and check that out if you want. But anyway, here's the steps that we outlined in the last video. Now this step 0 here, we didn't really mention that in the last video, and I put it in brackets because for the second derivative test it's not really as important, but for the first derivative test, you know, you set up that little sign chart and everything, so you kind of have to know where the function is defined. Because if there's a little interval that's outside of the domain of the function, then you don't really have to worry about doing that. You kind of have to think about the domain for the second derivative test, but again, it's not really as important, and largely it depends on what kind of application you're doing. And we'll do some application examples a little bit later. But anyway, you should just keep that in the back of your mind just in case it's something that is going to come up later. But for this particular example, x cubed minus 3x, that's just a polynomial, so it's defined everywhere, so the domain in this case is just all real numbers, so nothing to worry about. But anyway, step 1, the real step here, is find all the critical points of f of x. So we just want to find all the critical points, and how do we do that? We take this function, we take a derivative, and we did do this step in the first derivative test video with this example, but we'll just do it again here just to be thorough. But for the more complicated examples, we probably won't go through the process again, but there will be a link to the videos. So anyway, x cubed, the derivative is 3x squared, and then minus 3x, the derivative is minus 3. And if we want to find the critical points, we just take the derivative, set it equal to 0. Remember, we also want to know where's the derivative undefined, but this is also just a polynomial, so it's never undefined. But again, for the second derivative test, we only care about the critical points where the derivative actually exists. But still, you should find all the critical points just so you know, okay, I might have a critical point where the derivative is undefined, but I can't use the second derivative test there. And we'll see some examples of that later. But anyway, 3x squared minus 3 equals 0, so we can factor out a 3. If we divide both sides by 3, then we just get x squared minus 1 equals 0. Now there's a couple different ways to approach this, so we could factor and say x minus 1 times x plus 1 equals 0. So then that gives us x equals 1 or negative 1. So from here we get x equals 1, from here we get x equals negative 1. So these are our only two critical points. Okay? So that was step 1. So far not really different from the first derivative test, right? Just find the critical points. Now what's going to be different is here's step 2. Now we find the second derivative, f double prime of x. So the second derivative is just the derivative of the derivative. Okay, so if f prime of x is 3x squared minus 3, then f double prime of x is going to be 6x. And then that's it, because the minus 3, just a constant, so its derivative is 0. Okay? So that's it for step 2. Really simple for this example, but sometimes step 2 can be really bad, and we'll see some examples of that. And then step 3, evaluate f double primed of c at each critical point c where f prime of c exists. So again, critical point means the derivative is either 0 or undefined. So for all the points where the derivative is 0, all these critical points, evaluate the second derivative there. So we only have these two critical points, 1 and negative 1, and the derivative does exist at both of them, right? It's just a polynomial. So this example isn't too complicated yet. So now we just evaluate f double prime to 1, and what do we get? We get 6 times 1, which is just 6. Okay? And then we also evaluate f double primed, actually let's put that over here. Then we also evaluate f double primed of negative 1 was our other critical point. And that's 6 times negative 1, which is negative 6. Okay? So now That's it for step 3, evaluate f double prime to c at each critical point where f prime to c exists. And then step 4, basically this is just, step 4 is just apply the second derivative test. So if the second derivative exists, okay, so does the second derivative exist? Yeah, f double prime to 1 is 6, that exists. F double prime to -1 is -6, that exists. In other words, what that means is it's a real number. You know, you don't end up with anything dividing by 0, nothing outside of a domain, etc. So then we just apply the second derivative test. If the second derivative is positive, then you have a local min at the critical point. If the second derivative is negative, you have a local max at the critical point. If the second derivative is 0, then the second derivative test doesn't work for us. We have to try something else. So what do we have here? Well, f double prime to 1 equals 6, which is positive, right? So f double prime to 1 equals 6, which is positive. So what does that mean? That means that f of x has a local min at x equals 1. Okay, because the second derivative is positive there, and we talked about that a couple of videos ago, sort of why this tells us that. So here's one part of our answer. And again, we're only asking where these extrema occur. We don't care what they are, but if we want to know what it is, just take x equals 1 and plug it back into the original function. That'll give us our y value. But we did do that in the first derivative test video, if you want to check that out. Okay, so what do we have here? So that's it for this piece. Now we go over here and look at this other second derivative value. So f double primed of -1 equals -6, which is less than 0. So from the second derivative test, that tells us that we have a local max. So f of x has a local max at x equals -1. And again, we're only concerned with where this max is, not what it is. So this is where it is. It happens at x equals -1. And again, if we want to know what it is, just take -1 and plug it back into the original function. Okay? But for the purposes of this question, we don't care what it is, just where it is. Okay, so that's it for example 1. So it's a little more complicated than the ones we did in the last video, but still not too bad. So nothing really went wrong. You know, we just had 2 critical points and we were able to use the second derivative test for both of them. So it might be the case that you'll have critical points where you can't use the second derivative test, in which case you'll have to do something else like the first derivative test. So, you know, if you think back to the first derivative test video, the second derivative test was a little bit simpler in this case because we didn't have to set up the sign chart and evaluate the first derivative in a bunch of intervals, nothing like that. We did have to evaluate the second derivative at a couple points, but that was a little bit simpler. Also, we did have to find the second derivative, which in this case wasn't really bad at all. But sometimes finding the second derivative could be a little more complicated. So in this case, maybe the second derivative test was a little bit better to use than the first derivative test, but that won't always be the case. And we'll see some examples in the next few videos of different cases like that. So that's example 1.